Hello everyone, my name is Gao from University of North Carolina at Chapel Hill. I'm going to introduce our work titled Informative Feature-Guided Siamese Network for Early Diagnosis of Autism. I will first talk about the introduction and the second part is data collection. After that, I will introduce our method and the experimental results. The last part is conclusion and the future work. Let's start the introduction part. Autism or autism spectrum disorder is a developmental disability. According to the latest report of CDC in the United States, in 2020, 1 in 54 children aged 8 years was diagnosed as autism, and the autism was 4 times as prevalent among boys as among girls. Unfortunately, there is still no medical test for autism, and because the behavioral symptoms of autism will not appear before 3 to 4 years of age, such as repetitive behaviors or delayed speech development, autism cannot be reliably diagnosed until this time point. In addition, some research indicated that the early intervention services are useful for preventing the development of autism. Therefore, it is important to develop a system to categorize infants at risk of autism at the early stage. Recently, there are some works focusing on the autism diagnosis. However, there are some limitations for these works. For example, most of them rely on the predefined landmarks or biomarkers, such as the ratio of extra-axial cerebrospinal fluid to total cerebral volume, or the increasing rate in terms of cortical surface area expansion. Such predefined brain landmarks or biomarkers are isolated to the subsequent learning stage, and may lead to suboptimal prediction performance due to potential heterogeneity into standalone stages. Besides, these methods only use the information from intensity images such as T1 weighted image or T2 weighted image, ignoring the informative features from segmentation and parcellation maps. For example, some literatures indicated many regions of interest with significant differences between autism and normal groups. Therefore, it is highly desirable to employ the information from segmentation map and parcellation map. In the second part, I will introduce the dataset used in our research work. There are total 247 subjects collected from National Database for Autism Research, including 52 autism subjects and 195 normal subjects. For autism subjects, there are 40 boys and 12 girls, and for normal subjects, there are 109 boys and 86 girls. Figure 1 shows an example of the model input. The images from A to D are T1 weighted image, T2 weighted image, segmentation map, and parcellation map, respectively. It should be noted that the segmentation map and the parcellation map are generated by iBit version 2 Cloud, which is a publicly available software. The next part is the method and results. Figure 2 shows the framework of the proposed method. There are 4 components in our method. The first part is the feature extractor. In our model, the feature extractor is performed by a convolutional neural network to capture the diverse features from 4 types of inputs. As a plug-in unit, the feature extractor could be implemented by any convolutional neural network, such as ResNet or DenseNet. Then, the feature concatenation and fusion modules are used to further fuse and extract 4 features obtained from the inputs. After that, we utilize the subject-specific attention module to identify the autism-related regions in an end-to-end, fully automatic learning manner. Finally, we employ the Siamese network to identify whether the pairwise inputs are from the same class or not. The contrastive loss is to calculate the distance between the pairwise inputs, and in such a way, the distance will be small if the pairwise inputs are from the same class and large otherwise. Then, I will report our experimental results. In our paper, we present three metrics, including sensitivity, specificity, and accuracy. Our work is implemented by PyTorch framework, and the SGD with momentum is used as optimizer. The initial learning rate is 0.001 with cosine annually decay. We use a threefold cross-validation strategy to evaluate the proposed method. More specifically, we choose two-thirds autism subjects and two-thirds normal subjects as training set for each fold. Table 1 shows the results of ablation comparisons. The results show that the information from segmentation and parcellation maps could be a useful guidance for our task. According to the last two rows, the Siamese network could greatly improve the performance of module. Besides, the p-values presented in Table 1 also show the effectiveness of the proposed method. As shown in Table 2, we compare our methods with four state-of-the-art methods, although it's hard to directly make a comparison due to different subjects involved. As shown in Table 2, our proposed method can generally achieve more than 7% increase in terms of accuracy compared with method 3, 6, and 7. Although our method does not perform better than the random forest-based method, our method is validated on 247 subjects, which is much more than 38 subjects involved in random forest-based method. In addition to the quantitative analysis, we also show the attention maps generated from the proposed method. And we can observe that the cerebellum area and the insular area, which may be linked to some aspects of autism, is highlighting in the attention maps. And the last part is conclusion and future work. We summarize our work as four parts. Firstly, we propose an end-to-end informative feature-guided Siamese network for the autism diagnosis at 24 months of age. Secondly, we utilize the features from T1 weighted image, T2 weighted image, segmentation map, and parcellation map to distinguish the essential difference between autism and normal subjects. And thirdly, the subject-specific module makes the prediction of our method more reasonable. And lastly, the ablation experiments and comparison with other methods demonstrate the effectiveness of the proposed method. In the future, we will extend our work to 6 months old infant subjects and validate on multi-site datasets. Here is today's presentation. Thanks for your attention.